Hey everyone. These are the supplemental notes for lecture 5. There are a couple of examples because I read through the responses of on the survey. If you haven't done that yet, please do so. But on the survey, there's some people that were like, "Oh, can we get a little bit more examples?" So yeah, I'll do a couple more examples with 11.3. Hopefully that'll clear up some stuff, and then 11.4. There was something something kind of big I couldn't get to in lecture, so yeah, I'm gonna put that in here too. And then everything else should be covered by China, and then you guys should be ready for your midterm. All right, so let's get started with some of the examples from 11.3. Um, I just kind of like, oops, section 11.3. I just kind of like, either made these up or kind of like augmented some of the problems from the book. But hopefully this will do some justice and explain kind of how to figure out like the rectangular graphs of polar functions or vice versa, the polar graphs of rectangular functions. So why don't we start with let's do r of theta. So we're going to go from polar to rectangular. Okay, so I'm giving you a polar function. You got to tell me what the rectangular function is. And I mean, if you could describe it, that'd be great. So r equals, let's say, 4 sine theta. Okay, so I know from lecture you might be like, oh, I know that now. That's the sine one. It goes positive y-axis with a radius of 2. But I want to prove it algebraically now. Okay, the trick is we have to use our conversion factors. And if you remember factors, and if you remember, right, there was a couple to that we kind of need, right? There was the r cos theta is x, r sine theta is y. There was the tangent one. Tangent of theta is y over x. And then x squared plus y squared is equal to r squared. And these are like the main ones that you're going to use for these types of problems. So the thought process on these is like, how can I get these definitions to kind of look like these? Right, and the trick is usually, I mean, one of the common tricks is usually to just multiply both sides by r, and we kind of did this in class also. So hopefully this isn't like too like, oh, this is new, right? But yeah, that's a very common trick. But the idea is like we want what's given to us to resemble like one of the conversion factors, right? So like the only conversion factor that deals with sine is this one right here, right? We need an r, and then also this single r is useless to us, but r squared is useful to us, right? So that's the kind of stuff you want to look out for. So this becomes r squared equals 4r sine theta. And now that we have some things that fit our definitions, we can kind of just make the substitution and see what we get. So on the left side, we get x squared plus y squared is equal to the right side, which is 4 times r sine theta, which we just said is equal to y. So 4 times y. So now we got something in terms of x's and y's. You're gonna oh my gosh, you're gonna bring the y terms to the left side. And you're going to see that this is actually another completing the square problem, right? I can, if I divide the b term in half and square it next, right? Yeah, okay. So you take 4, divide it by 2, you get 2, and square it, you get 4. And that's what you're going to add to both sides. I can rewrite this now that I completed the square, as y minus 2 quantity squared. And the right side is 4. So what did we just do? We just converted the polar function r equals 4 sine theta into x squared plus y minus 2 squared is equal to 4. So this is a circle with a center of 0, negative 2. So it's a circle that, I'm sorry, 0, positive 2. So it's a circle that's been expanded upwards, has a radius of 2, and yeah. So there it is, right? So hopefully that gives a little bit more perspective on these types of problems. I'll do one more. Let's see here. r is equal to, I'll do an easy one, a quick one, secant theta. And you're like, oh shoot, secant, not the reciprocal trig functions, anything with that. But just remember, we want this to resemble our, whatchamacallit, our conversion factors, right? So we're actually not going to multiply by r on both sides this time. The reason for that is because we don't have a conversion factor for r secant theta, right? There's no conversion factor for r secant theta, so we need a different strategy here, okay? Well, I know that secant of theta is the same thing as 1 over cos theta, isn't it? And if that's the case, well, I can do some algebra here. I can multiply cos theta to both sides, and oh my gosh, I have r cos theta on the left side is equal to 1. And this should look familiar. That's one of our conversion factors. R cos theta is x equals 1. Oh, snap. John, you're telling me that r equals secant theta is just a vertical line at 1? Yeah, it is. Pretty gnarly, right? Yeah, okay. All right, I'll stop that. All right, so let's move on to the next thing. So we did that. This is probably going to take the majority of the video. It's going to take a while. I guarantee it. So 1.11.4. We're going to talk about finding areas between two polar curves now instead of just singular areas, right? Because I did that during lecture where we found like the half semicircle area, right? Making sure that we consider bounds and all that stuff. So we're going to take this a step further and find areas between two polar curves. So let's say, okay, I'm just going to do example 3 from the textbook. This is on page 664 on the PDF. So it says to find the area of the region, inside. Okay, so watch out for these keywords. Inside r equals 2 cos theta. But outside r equals 1. All right, outside r equals 1. So you can definitely expect a problem like this level on your midterm and stuff. But in the fall, they might do more complicated other polar functions. All right, so let's first figure out what these two graphs look like. Okay, I'm just going to do the abridged version for time's sake. R equals 1, if you think about it, it means that no matter, right, because it's this, no matter what I plug in for theta, I'm going to get 1, a radial length of 1. So if I start at 0, I'm going to get a radial length of 1. If I go to pi over 4, I'm going to get a radial length of 1. If I go to pi over 2, I'm going to get a radial length of 1, and so on and so forth and so on and so forth. And what ends up generating is a perfect, oh my gosh, a sort of perfect circle for me, but it's a circle with a radius of 1. Okay, so that's the first one. The other one, 2 cos theta, if you were paying attention during class, this is going to be a circle with radius 1 that expands outward towards the positive x-axis. So it's going to look like, I'll do this one in red, like that. Ugh, whatever, it's good enough, right? So this one, I'll call this R2, D2, sorry, and this one is R1. Okay, so R1 is in black, R2 is in red. And we want to find the area of the region that's inside the red one, but outside the black circle. So what section is that representing? Right here. Okay, so we are trying to figure out the shaded green area. So what are we going to do? How do we do this? Well, when you're finding the region, or when you're finding like area between two polar graphs, there's kind of like a rule of thumb that you kind of follow. It's not all the time, but it should be like reminiscent of what you guys did in chapter 6, like top minus bottom. There's like this outer minus inner thing going on that usually you kind of like do for these types of situations. And what I'm trying to say is, what we're going to do is find the area of one of the functions and then subtract the inner other function. And in this case, right, I'm gonna find the area I can find the area of the red, right, and then kind of like subtract away like the black. But there's kind of like a whatchamacallit, like a hurdle that we have to kind of get through first. And what that is figuring out the intersection points. I'll do this in blue. Figuring out these two intersection points, right? Those are going to be some theta values, okay? Because once we figure out those two intersection points, in fact, those are going to be like our bounds of integration that we're interested in, right? Because think about it. Once again, it's kind of like think about a sweeping motion, right? Imagine that like this is a radar thing, right? And it starts at this theta value, and it's gonna sweep until the second theta value, right? What is it gonna sweep? It's gonna sweep both the black or the red, right? And what we're gonna do is use this outer minus inner idea, and figure out like which one's the outer and inner. Hopefully, I mean, you guys probably figured it out already, right? The outer function in this case is going to be the red one, and then the inner function is going to be the black one, right? So if I can kind of, so the area of the green is going to equal the like area, like the sweeping area of red minus the oh, it's already in black, area of black. All right, I hope that makes sense, right? I'll shade in the right. So that black area we gotta subtract away, and then like the red area is like the total area. Maybe I should have done that one first, and then we have to subtract away the black to get the green. I hope that makes sense, right? So first things first, we have to figure out the theta values, right? We got to figure out, well, where do these two functions intersect? And hopefully that kind of like rung some bells, right? We got to set the two r's equal to each other, r1 equal to r2. So what is that going to become? This is going to become 1 equals, what is the other function? 2 cos theta. 2, handwriting is disgusting. 2 cos theta. And hopefully you guys know how to solve this. This becomes 1/2 is equal to cos theta. And when does theta produce a 1/2 value? Well, if you think about the unit circle, right? When does cosine theta produce 1/2? That's asking when is the x value the shorter of the two, right? Because if you guys remember the unit circle, right? Like 30, 45, 60, the shorter x value is here, as opposed to here, right? We all know that the middle one is just root 2 over 2 comma root 2 over 2. So we want to know when is the theta value, am I doing this right? Yeah. When is the theta value the shorter, which theta value gives you the shorter x value? Yeah. And that's going to be pi over 3, because this one's pi over 6. Right? So we want the shorter x value instead of the longer x value. So yeah, it's going to be like multiples of pi over 3. So that means like here, here, it should be here and here. Okay? And in fact, luckily we have like a perfect unit circle here. I think they probably did that intentionally. We want this theta value. I'll do this in red. We want this theta value and this theta value. Well, this one is pi over 3. I just said that. What's this one going to be? It looks like negative pi over 3. Okay? Please be careful. Do not say pi over 3 to, what is that? What's pi over 3 plus 3 pi over 2? Whatever that is. Is that, what is it? 5 pi over 3? Yeah. So it is not pi over 3 to 5 pi over 3, okay? Pi over 3 to... Why is it not this? Because this is the wrong sweeping direction, right? We're sweeping the wrong side of the circle. We want to sweep from negative pi over 3 to pi over 3. Oh, that's pi over 6, I'm sorry. To pi over 3. I hope that makes sense. Okay, you have to choose the correct sweeping like direction. All right. So for this problem, we're gonna go negative pi over 3 to pi over 3. So we found our bounds. That's great. That's awesome. That's like the hard part. Is it the hard part? Okay, it's one of the hard parts of these problems, right? So we're going from negative pi over 3 to pi over 3, and kind of going back to this thing right here, right? We want the area of the red, meaning we want the area of R2, D2. So R2 is 2 cos theta quantity squared, right? Oh, I can't forget the 1/2. What that's going to give us is the sweeping motion from theta 1, so negative pi over 3, all the way up to pi over 3 of just the red, right? So, and that's too much. We want to, now we have to subtract away the area of the black. So we're going to subtract, once again, 1/2. The black one is 1, right? 1 squared, r squared, right, d theta, from the same bounds. I could have combined them into one integral if I wanted to. It's totally up to you. But to me, this makes more sense because this shows like the red minus the black. All right. And from here, we just integrate, right? We just do our thing. We're going to square the 2. So it comes out as a 2 integral from, so cosine squared theta. Is it easier to combine it? I guess it kind of is, right? So this is going to become cosine squared theta minus 1. Whoops. Minus 1. Minus 1 d theta from negative pi over 3 to pi over 3. And just like in class, right, I really, really hope you guys know your half-angle formulas because they save you at these moments. Okay, like rewriting cosine squared and sine squared. So in this case, we're going to rewrite cosine squared. All right, and we're going to get 1/2. Oh shoot, what is it? 1? It's 1 minus or plus? I think this one's plus, right? Cosine 2 theta minus 1 negative pi over 3 pi over 3. 2's cancel out. And what are you left with here? Oh, d theta. It looks like I'm left with, oh, the 1's cancel out, which is nice. And then I'm integrating cosine of 2 theta. That gives me 1/2 sine of 2 theta. Let me just double check that, right? Because the 2 comes out, and the derivative of sine is cosine. Yep. And we're going from negative pi over 3 to pi over 3. Oh my gosh, no, I messed up. I know I messed up. Okay, all right. Sorry. Let's let's keep them separate. I think that's gonna be. How do I? Oh nope. Let's keep them separate. Why can't I delete this? Can I delete this? Just go away. I don't know why I can't delete this. What? Okay, or whatever. Okay, so let's keep them separate because I think there's like a factor of 2 that I just totally ignored because of the. Okay, so I'm gonna keep them separate and then I'm gonna integrate them separately. All right, so we get 1/2. No, a 2 comes out, right? Yeah. So I'm gonna get 2 integral negative pi over 3 pi over 3. This becomes cos squared, right? 4 cos squared. The cos squared becomes 1/2 1 plus cos 2 theta d theta, which is nice because these are going to cancel out. And then this becomes minus 1/2 theta from negative pi over 3 to pi over 3. All right. And then, wait, is this recording? Oh, yes. Okay. And then we integrate the left piece. So it becomes theta plus 1/2 sine of 2 theta from negative pi over 3 to pi over 3. The right piece becomes minus 1/2 What is that? That is upper minus lower. So it's pi over 3 plus pi over 3, which is 2 pi over 3. This one's going to become upper minus lower. So we go pi over 3 plus sine of 2 pi over 3. That is the higher one. So it's root 3 over 2 times 1/2 minus negative pi over 3. Oh my gosh. Plus negative 2. So sine of negative 2 pi over 3. That is negative root 3 over 2. My gosh, this is a pain in the butt. Minus this guy, which is pi over 3. Let's clean this up a little bit here. We get pi over 3 plus root 3 over 4. And then this becomes plus pi over 3. And then plus root 3 over 4. Minus pi over 3. Oh, thank goodness things cancel out. And this becomes root 3 over 2 plus pi over 3. Please, I really hope this is right. Oh my gosh, I'm right. Oh, all right. Whew. Man. So yeah, the hardest part is I lied. The hardest part is probably this, plugging in and hoping that the negatives don't kill you. But yeah, that's pretty much it. Honestly, this piece I'm not as worried about. You know, the whole plugging in and getting to the right answer, or whatever. I'm more worried about with the setup and like all that stuff, because like this, like the bottom piece, like you can practice that and like that's easy to understand. The top part where you have to do the setup and figure out which one's the inside, which one's the outside, you know, that's the tougher part. All right. I'm looking at the clock. Holy poop, it's 22 minutes. I'm gonna just set up one more. I'm not gonna do the second part like I did here. I'm gonna set up one more problem for you guys, and you guys can finish it on your own. Example, I don't know, 2, sure. And hopefully this one is a little bit better. So let's say I want to find the area inside, that's not inside r equals 1, and outside the cardioid, or the butt, 1 minus cos theta. All right, so if I draw it out, I have on this one in blue, it's r equals 1, and then 1 minus cos theta. Okay, I'll talk it out for you. Negative cos theta means we're expanding out to the left, and since the ratio between this and this is 1, it's going to create like a cardioid, which looks like this. It's not too bad, but yeah. All right. So I want to find the area inside the circle, but outside the cardioid. So what is that looking? Where am I looking, right? I'm looking outside the butt, right? That's this piece right here, this shaded area. Okay, we're going to do the same thing, right? We need to find the intersection points, which is, it looks like here and here, right? We're going to find the intersection points and then sweep the proper areas, right? So we got to do outer minus inner again. In this case, the outer is going to be blue, and then the inner, I guess, would be the green. Okay, so like I said, I'm just going to do the setup. Well, to figure out the sweeping area, it looks like, right, I'm going to use r equals 1 as a reference. Oops, I shouldn't have done that in green. R equals 1 as a reference, right? Well, that point for r equals 1, it looks like negative pi over 2, and this point looks like pi over 2, right? Because at negative pi over 2, the radius is going to be 1. At pi over 2, the radius is also going to be 1. So, or you can set the two functions equal to each other like we did in the last example, right? You get cosine theta is equal to 0. And when is cosine 0? It looks like, you know, at all multiples of pi over 2, right? So that, yeah, so that fits negative pi over 2 to pi over 2. Now we do our setup, the integral from negative pi over 2 to pi over 2, 1/2, can't forget that. We're going to do the outer function, which is 1 squared, minus the inner function from the same bounds, which is the cardioid. 1 minus cosine theta d theta. Oh, can't forget the squared. And that's it. That's as far as I'm going to go just because this video is so freaking long. You can do the rest on your own, okay, if you want to, right? You're going to square the 1 and, integrate it. I highly recommend that you integrate like separately. I feel like that way, like, I don't know, leads to less errors. I don't know, but that's just me. It's totally up to you. If you want to combine these, you can. I just combined them wrong in that last example. I think I forgot to factor out the 1/2, and then like maybe, yeah. So, and like, don't forget to distribute on this one. So, with the integration steps, okay, don't forget, I see it right now. This is going to become cosine squared. So you're going to need that half angle formula again, it looks like. Okay, but everything else should be very doable. You guys should get to the right answer. Just focus on the setup. It is so important that you guys do the setup properly. Okay, so that's it for this video. If you have any questions, once again, please reach out. Come to Monday's class early so that we can go over anything that you guys want to go over. All right, have a great weekend, and I'll see you guys on Monday.